But anyway, I will still provide a little bit of context, maybe more from a technical point of view to get us started. So on the left-hand side, it is what we are still commonly having nowadays. It's a regular VM where its memory is visible to vendor, even with traffic encryption or disk encryption enabled for the VM. And on the right-hand side, in the confidential VM case, we have a VM where its memory is encrypted in the sense that the host is unable to understand the data sitting within the VM. So I have highlighted the color using green as the plain text that will be visible to inside of VM or outside of the VM. And purple color is the ciphertext that the data won't be seen by the host. So to further demystify what CVM is about, first of all, it's from the user perspective, it has the same abstraction of as a regular VM. So it's just the same way as using a typical KVM machine. And secondly, in terms of the memory management setup, there will be one bit in the page table entry that is used to control the encryption state of the guest page. And by default, all pages that are used by the VM is encrypted. You may ask, for example, how does the encrypted page get decrypted? Well, and here I've attached a diagram. It's sort of a bit too low level, I suppose, yeah? And it's decrypted automatically by hardware when loading into CPUs, LLC, and registers, and vice versa for the other direction. Yeah. So as a result, the pages are protected from unauthorized manipulation. And then there's also a new secure module for the VM exit path in the case of CVM. So what we had before is that VM exit will occur when the host is trying to do some privileged operations, and the hypervisor will handle it before running VM enter to return to the VM context. But however, for CVM case, the VM will instead first do an exit into an intermediate state, so-called the secure module, before doing the actual VM exit return to the hypervisor, and vice versa, yeah, for the other direction. Also, as we can see, the secure module is responsible for masking sensitive registers and to restore sensitive registers as well. So using this feature like this obviously will come at a cost. We did some couple of experiments on both CVM and non-CVM environments and trying to obtain more insight of how the networking performance is impacted. Here we used the term TEE, which stands for Trusted Execution Environment. It seems like it's being used interchangeably nowadays with CVM context in confidential computing domain, but you get the idea, yeah. So the first experiment that we did, which is very standard, we ran iPerf with setting of using TCP 32 threads. So we see that in the CVM environments, the performance is around 10 times slower than the non-CVM one. While on the right-hand side, we ran engines with TLS version 1.3 enabled for different packet sizes. We can also see that the performance drop in terms of number of requests is very high. So what we're going to do now is we are going to do a breakdown and try to find out where the performance overheads are coming from. So the picture here shows the data flow of the packets in both RX and TX direction. So for RX direction, the NIC initially received an IP frame with TLS encrypted payload. And now for CVM environments, the buffer will be DMA write into an unencrypted memory region called software IOTLB, which we have highlighted green color here. After that, the kernel will copy the data from the software IOTLB's buffer out to a memory region that belongs to the guest. And after going through the kernel stack, engines will receive the packet. And on the other hand, for TX direction, when engine tries to send a packet, a TLS encrypted payload is initially located in the encrypted memory or page inside the gas. And then the kernel will copy this buffer to the software RTLB. And at the end, the NIC will DMA read this buffer before sending it out. So in summary, you can see that the purple color region are, again, in the encrypted memory, where only the gas can see the real data, while the green color region is shared between the gas and the host, and both can see the data. So here for a short summary, so we can see that the additional overheads are mainly introduced by, first of all, a longer VM exit path when executing privilege operations. So for CVM case, the VM exit cost is gonna be at least a couple times higher in terms of the number of cycles comparing to non-CVM case. And also what we saw earlier is that the extra memory copy happen in the software IOTLB bounce buffer, which ultimately resulting a so-called double encryption problem, as we can see that TLS decryption is also needed after that, such that the gas can access the data in plain text. So here, how can we use DPDK to optimize the two problems that we just talked about? Well, DPDK PMD operates in PO mode, so the number of VM exit can be reduced. And also the extra memory copy can also be kind of taken away when which we will talk more about this a bit more later. So this couple optimizations is achievable by, first of all, patching the CVM Linux kernel to allow DPDK to use the unencrypted memory to do DMA. And on top of that, we also need to patch DPDK to manage both encrypted and unencrypted memory. And last but not least, we also need to modify DPDK applications to use this new, whole new memory management system. We have tackled these problems last year, and we had presented last year in DPDK 2023 as well. So if you, any of you still remembers, and interested in knowing like what we did last year, so please feel free to download the slides again to give it a read, or just, of course, welcome to send us an email and we can talk more about that. Yeah. So after last year, we did some work to kind of try to adapt DPDK into this CVM environment. However, we still ran into some challenges where when we are trying to put all these technologies into real use. And first one is that the latest CVM technologies lack users mode MMIO support, whereas DPDK requires it to talk to the device. And secondly, since there are many existing applications that are not based on DPDK, therefore the cost of porting this and support this feature is going to be high. So what we did was that we first patched the CVM kernel to enable user mode MMIO. Then we use DPDK-based Userspace network stack with built-in TLS enable instead of kernel stack. Well, as you can guess, yeah, VPP was used in our approach. But I assume many of the audience here are already familiar with VPP. But still, I will just give it a quick overview on VPP, just in case. Yeah. So VPP is a DPDK-based Userspace networking stack. So instead of traditional scalar packet processing, it leverages vector processing to handle batches of packets, similar to what we've been working on over the last few years, or even this year's, for our RT lib graph. It also supports multiple networking protocols and can be used to run on standard commodity hardware. And it also supports using LD preload to an existing applications, socket API calls, which allow the application to use DPDK stack without rewriting the application. So here we go again. Yeah, we will go through the RxTX data flow again, similar to what we just did earlier in this presentation. So on the right-hand side, there is a graph highlighting the Rx direction, which it can be used as a reference. Yeah, and TX direction is very similar. Yeah. So for Rx direction, again, the NIC will receive the IP frame with TLS encrypted payload. And now, instead of doing DMA write into the software IOTLB bounds buffer, this TLS encrypted packet will be DMA write in a packet mbuf pool that is sitting in an unencrypted zone. And since it is TLS encrypted, we are not concerned that we will have any security breach, even though where this packet is at now is shared between the host and the guest. After that, the packet goes through the Userspace network stack, in other words, the VPP stack. And here comes how the memory copy we had earlier got kind of taken away. So when we do a TLS decryption, initially this TLS encrypted payload is in the green area, right? The unencrypted page. And when you are trying to do some kind of cryptographic operations, you need to specify the source and the destination address. So here, when we are decrypting this payload, we specify the destination address in the sense of it will be in an encrypted page. So you can see from the diagram where we zoomed in this operation, and the packet will look like it got jumped from the unencrypted page to the encrypted page, while at the same time it will also be decrypted because of the crypto operations for the TLS. Yeah. And finally, because Nginx and VPP will share a memory region, Nginx will receive the payload in the encrypted share zone. Whereas for TX direction, the procedure is very similar, but just the other way around. So now Nginx tries to send a packet, right? It will send the HTTP payload to the purple share memory region again in the encrypted zone. Then payload is encrypted to the unencrypted zone in VPP process space, just like the zoom-in diagram again, but just the other way around. Yeah. And after that, the packet will just go through the VPP network stack and get sent out at the end. So now let's do some performance evaluation on the approach we just shared. So for our settings, we use 8 workers in Nginx, 1 thread in VPP with TLS 1.3 enabled, running on an Intel Super Rapid CPU. And for the performance, so we can see that the 2 blue colors bars are the one that we had in the beginning, where it just merely runs Nginx without DPDK on CVM or non-CVM environment. And the purple bar is what we have now. So comparing this DPDK approach with the kernel TE1, we can see that we have around 3 times higher number of requests for small packet size. And as the packet size increases, the performance increases rate slowly decreases too. Whereas comparing the DPDK approach with the kernel non-TE1, we can still see that there are still a small gaps for the DPDK approach to catch up. This is possibly because of we might still have some VMXs triggered by other components, for example, IPI. So here is some of the future works that we have also put down. So first one is to optimize any current VM exit pathing. And then second one is the one that I just mentioned, to reduce any non-DMA induced VM exits. For example, the VM exit that is triggered by IPI. And also it would be nice to extend current solution to storage application in a similar manner. And yeah, that's all from the presentation. And yeah, if you have any questions, yeah.
Hey, William, Alex Kozary from NVIDIA here. Do you have numbers for the DPDK solution with unencrypted VM? So just to compare the gain there.
Wait, sorry, which slide were you referring to?
The last one with the graphs.
Yep.
Yeah, so you have the DPDK plus VPP in the secure environment.
Yep.
Do you have the same numbers for the unsecure environment? So just to compare DPDK with the DPDK.
Yep, so the purple bar is what our approaches gave, right?
Yeah, and it's TE environment there, yeah?
Yep.
It would be nice to have the DPDK plus VPP in non-TE scenario as well, just to understand what's the performance penalty for the DPDK in the
But
TE.
it's hard to compare in the case that you just mentioned, right? Because in non-TE environment, we don't really have the we don't really use the software RTLB buffer, so it will, and then you also lost the purpose of what you wanted, which is the security that you want.
Yeah, just to understand the price of the security.
Yeah, maybe we will also run that. Yeah, but thank you. Yeah.
Yeah, thanks.
Yeah.
Otherwise, it was cool. Thank you.
Hey, this is Edwin from Intel. What is the blue bar exactly? So follow-up question on that.
Sorry, which one?
The blue bar. So.
Which blue? The lighter blue? Or?
Sorry, yeah, dark blue. The
sorry. So the dark blue is what we are having now, and just a normal VM from QMU.
Okay,
without any like encryption.
Okay, but still Nginx.
Yep.
Okay.
Yep.
Okay. Okay. So I can see this work for TLS traffic, right? But what do you do? What do you do for non-TLS traffic?
So that's a really good question. I should have mentioned it in the presentation as well. Well, for CVM setup or like case like this, like it's kind of like pointless to have TOS non-TOS setup, because like let's say you have a VM running on a host, a non-TE environment. Well, sorry, a TE environment, yeah. And you are having non-TOS encrypted packet coming to the host. So obviously the host can see it, right? If you get what I mean. So in this approach, like TOS is sort of like a requirement that you have to use to, yeah.
Okay, so somehow you have to enforce it. Maybe I thought you could do it with some form of queuing, right? You could potentially do something with so for example, like most NICs have some ability to detect traffic and then steer to a certain queue, but I still have to think this through a little bit, how you would set that up, right, to make it more generic. But yeah, I'd love to have your thoughts on that sometime.
Thank you.
Yeah.
Hey, yeah, thanks, Konstantin from Huawei. And this is one request per connection, I suppose, right? Is it these performance numbers? I wondered, do you have anything with bulk transfers? Would it
Sorry, could you repeat?
Well, I suppose this test environment, right? This test case, you're using one request response per connection, if I understand correctly, or not. Basically, what I'm interested in how it would look like if you do have a lot of bulk transfers. Would it still be the same, or would it be different? And if yes, in what way? When kind of you have each request, let's say, in response you have to transfer several megabytes of data, not 1,500 of bytes.
I'm not sure if we have. I mean, like the graph, like the diagram here, probably just show the peak of the performance. But yeah, I think my colleagues Yue and Zhifei are online. So if they want to add anything to this question.
First, we see that you are using VPP, probably because that's very convenient, all the features that you need. But don't you think that you could get better performance if you manage to use just DPDK with a TCP TLS stack?
I think the majority reason that we use VPP is exactly what you just mentioned. Like it's convenient and and yeah, and what ultimately we wanted to test was, I suppose the TE features, like the software RTLBs, and the changes in the VM exit path. And we think that like current approach and current setup would do the job. But yeah, thanks for the bring up. Yeah, maybe we will also use use DPDK to like cover it like in a broader. Yeah.
Okay. I'm just checking if you are interested to work in such a solution.
To what?
To avoid using VPP. Yeah, that's the question.
Yeah. I mean, we could try. As I said, like, and now we have like more developers working on libgraph, right? Yeah. So maybe it's also a good way to.
Yeah, there is someone in ByteDance working on nice TCP stack, libTPA, for instance.
Oh, sorry. Could you repeat?
libTPA.
libTPA.
TPA, yeah.
TPA.
It's a TCP stack. Done in ByteDance.
Not anything that I'm aware of now,
Okay.
but maybe we need to communicate like internally for that. Yeah.
Okay, let's connect. Different question. I remember from last year that there was a need for new functions in DPDK to support confidential computing.
Yeah, I think it was the Userspace MMIO that we mentioned last year. Yeah, so last year we were, like after our talk, we also needed to do some work to support Userspace MMIO for different vendors.
Okay, so there is a need for a new function in DPDK for that?
Oh, no,
No. Yeah,
not new function in DPDK.
Yeah,
no.
okay,
Yeah.
it's completely transparent.
Yep.
Yeah, thank you.